Okay, I'd like to give you a couple slides here about some important applications of lenses. The first one will be a lens in front of a detector. And in showing this example, it'll allow me to talk about a cone of rays, and it'll also allow me to define the numerical aperture. Numerical aperture is a big, important concept in our fiber optic systems as we talk about the properties of fiber. And in the next slide, second slide here, I'll actually derive the equation for the numerical aperture of a fiber. So in the first case here, we're going to consider a detector. And it'll have some finite extent. We're going to assume that it is aligned on the optic axis, perpendicular to the optic axis. And we're going to go ahead and put a lens out in front of that detector. And we're going to put that lens at a distance equal to the focal length of the lens from the detector, so that the detector is actually in the focal plane. And the focal point of the lens is on the axis where the detector meets the axis. And so we know that parallel rays coming into this lens will be brought to a focus at this point, at this focal point, as so. I won't show them continuing on any further. We'll assume they've hit the detector here. We also know that we can take parallel rays which are not perpendicular to the optic axis, and that they will also be brought to a focus. What I'll do then is I'll bring in a ray which is going to hit just the very edge of the detector here in green. And we know now that rays parallel to this ray, which goes right through the center of the lens as a principal ray, rays parallel to this ray are also going to be brought to a focus at this point. So I can draw some rays parallel to it coming in green, let's say, and that these rays will all be brought to a focus at the edge of that detector. So here's another one. Okay, so the reds have been brought here. In other words, what happens is there's a maximum angle off of the axis through which rays will be brought in and actually hit the detector. Rays that are brought in at a larger angle miss the detector entirely. And so what we're going to do is we're going to sort of characterize this situation by what we call a cone of rays. So the cone of rays, we can think of it as, so let's go ahead and draw this detector again, sort of smaller here with our lens out front, and we know now that this is the largest angle at which some parallel rays, some rays can be brought into this lens and still hit the edges of the detector. And so in fact this angle will define a cone. And any ray that comes in within this cone is going to strike this lens and be brought into this detector. Actually, the cone, so if I bring in rays parallel to those two, they will also be brought in and hit the detector. Okay, so let me draw these two. And maybe I'm running out of colors here. Maybe this one should be blue. And another one parallel to it could be brought in. I'm sorry, this is blue. Yikes. Parallel to that one and hit here. Okay, so this is red. Okay, so these red rays are focused at the top of the detector. The blue rays are focused at the bottom of the detector, and the green rays are all within that cone, and they also all hit the detector. And so this cone of rays is characterized by its half angle. I'm going to call this theta C also, is the cone angle. Okay, and so they all hit that detector. So all of these rays, I guess I messed up the picture here, are going to hit that detector. I'll draw it again real quick here on a blank piece of paper. So I've got my detector here, I've got my lens here, and I can bring rays in at this maximum cone angle, like this. But then anything parallel to that is also brought in and focused to that same point. So these rays in green are focused up here. The rays in blue are focused down at the bottom. And so anything within this cone is then focused into this, onto the surface there. So this is that cone right here. And that cone is characterized by this cone angle, theta c, which is the half angle of the cone. Okay? Okay, so this allows us to think of cones of rays. And what we're going to do is we're going to go ahead and define what's called the numerical aperture. And immersed in a medium of index n, a cone of rays with a cone angle theta c will have a numerical aperture n sine theta. So theta c is the half angle of the largest cone accepted. What does that mean? Well, we've seen here that in this case of the detector, if our rays are outside of that cone, they miss the detector. In other words, they're not accepted by the system. Okay? So in our case, accepted means they hit the detector. Okay, in the case of an optical fiber, when we say that the ray is accepted, what we'll mean is that it does get brought into the core of the fiber as a ray undergoing total internal reflection. In other words, as a ray that is guided by that fiber. Okay, so we're going to define the numerical aperture, and what I want to do is I want to convince you that based on Snell's law, the numerical aperture of a cone of rays doesn't change when it hits a planar interface and hits perpendicular to that planar interface. So the geometry is a little bit hard to show here, but I'll do it. Here's an interface from N1 to N2. Again, we're going to assume N1 is larger than N2. And so we could think of a ray, a single ray coming in here. This is the normal. And so this is the angle theta 1. And the ray will be bent away from the normal because N2 is less than N1. So the ray will have a theta 2 larger than theta 1. And you can think of this ray as characterizing a cone coming in at theta 1 and then going out at theta 2. Okay, so we can think of this as characterizing cones. But because of Snell's law, N1 sine theta 1 is equal to N2 sine theta 2. In other words, the numerical aperture of this cone is equal to the numerical aperture of this cone. One of your homework problems asks you to show that in some detail, and I want you to go through this geometry and convince yourself that's true. Okay, let me go ahead and give you a derivation of the numerical aperture of a fiber. I'll go quickly here because I may be running out of time. Basically what we're going to do is we're going to bring a ray in. I'm going to draw a picture of the end face of the fiber. So this is the end face of the fiber. This is the air outside here. This is the core of the fiber, and there's cladding outside. And so what we're after is we're after a ray which characterizes the acceptance angle the acceptance cone of the fiber. So when we say that the ray is accepted into the core of the fiber, we mean it undergoes total internal reflection at the interface between the core and the cladding. Remember, the core index, N1, is greater than the cladding index, N2. And we're going to assume that the index of the error is 1. Okay, so we're interested in an array which comes in at some as some cone. This is the edge ray of a cone, as in this picture up here. And we're going to ask you, what is this angle here? What is the maximum angle such that this ray, once it gets into the fiber and hits the core cladding interface, undergoes total internal reflection? In other words, we're going to ask for this angle to be the critical angle. We're going to now call this one on the inside of the core alpha, and the one outside here alpha prime. And I'm going to go ahead and apply Snell's law, and I'm going to say that the critical angle, first of all, I'm going to write down the equation for the critical angle. It's the arc sine of N2 over N1. We know that. We also know that alpha is 90 degrees minus the critical angle. We also know that the numerical aperture of the fiber is equal to N1 sine alpha, where this numerical aperture is characterizing this cone of rays inside the fiber. We also know that that numerical aperture, okay, so let's just plug in here. Let's just plug in, and we're going to get N1 sine of 90 minus theta critical, 90 degrees. And we know that sine of 90 minus an angle is the cosine of an angle. But we also know that the critical angle is the arc sine of N2 over N1. And this is easy to calculate from your calculus class. We know now that this is the square root of N1 squared minus N2 squared. Okay? But we've also shown in this previous diagram that the numerical aperture of a cone doesn't change upon hitting a planar interface normal to that interface. And so we know that this numerical aperture inside, let me call it numerical aperture 1, is equal to the numerical aperture on the outside. Now let me call it numerical aperture in and out. Okay, but numerical aperture in is equal to numerical aperture out. And now on the outside we're going to consider this cone coming in. Okay, and so hence the numerical aperture of the fiber is the square root of N1 squared minus N2 squared. And this is a positive number because N1 is greater than N2. So that's the calculation. Thanks.